Hey, Patrick Sullivan here, and I want to introduce you to the framework See It, Say It, Symbolize It in terms of transformations of functions. So, what is the See It, Say It, Symbolize It? It's an idea that I've thought about fairly deeply with respect to elementary math content, but I want to extend it into both middle school and high school content. So, today I'm going to talk about transformation of functions. So, the first thing, the See It part is what is the representation that can be best utilized to really see to see the idea, make it most explicit. So it's really a choice of fronting a representation or an activity or an experience that's going to give students the best chance of seeing the idea that or to illustrate the concept that you want them to see. The second part of that is the say it part, and that's really the conceptually consistent language that you want students to associate with what they're seeing. And oftentimes, we jump from the concrete to pictorial to the abstract, but we really don't incorporate the language. And I think a language is a critical piece to moving from what we're seeing to what we're seeing in terms of the symbols or what we're symbolizing. The last part of this is the symbolizing it. So really, it's when you look at a set of mathematical symbols, what do you see when you look through it? So we're going to build that. Oftentimes we start with the symbolizing, and that sometimes hinders students' ability to look through it because all they see is a cue to do something. So let's take an idea here. And your job, what I want you to think about, and again, anytime during the video you feel like you need to pause to engage in the activity first, please feel free to do so because it may deepen your experience as you do this. So first of all, think about the prompt here. Create a graph that moves this function relationship 3 units to the right. So take a moment and think about what that might look like. So now we've moved the ordered pairs that we're seeing, although it's the entire graph that we're looking at. The entire plane is being moved 3 inches to the right, but we're going to focus on those 5 ordered pairs. So again, at this point, you should be able to see an idea that's happening here. Something's going on. And oftentimes the communication is the challenging. So students will often say, typically, these are the statements I'll make. Each point in the plane is translated 3 units to the right, or it moves to the right 3 units, or the shape of the graph does not change. Those are some of the big ideas that they typically see. But we want a little bit more precision of language. Again, this is really about a big part of this is mathematical practice 6, which is attend to precision. And in this case, we're going to talk a little bit about language. So it moves 3 to the right really isn't describing, what is the it is part of what we're trying to better understand. But since it's a functional relationship, you have input and output values, and you have to ask yourself, are the input values changing? Are the output values changing? And how to interpret that and describe that. So again, each point is translated 3 units to the right. Okay, that's a little bit imprecise, but to be more precise here, we have a little bit of a better statement here. The graph is formed by shifting each corresponding point on the original functional relationship 3 units to the right. But again, it's lacking that specificity that we want to hear. In this particular case, that specificity has to do with, and that precision has to do with what's happening to both the input and output values because they're changing simultaneously. So in this particular case, the input values are increasing by 3, while the output values remain the same. So now that we have the see it, we have the say it, we're going to move on to the symbolize it. So how would you describe this functional relationship using algebraic symbols? And if you're like me, you probably just memorized this idea, but I've always struggled with this idea of why, if I'm moving it 3 units to the right, is the functional relationship why is it x minus 3 squared instead of x plus 3 squared? And I know that's a question students ask. By the way, I don't just generically, as students are starting out, just ask them to determine the symbolic. I will give them choices. And so these are 4 examples of choices that I would typically give them because, again, I want to engage them in productive struggle. And oftentimes they're learning about the symbolic and the coding of the symbols. So for me, I'm giving them a choice. And so they have to make a decision between which of those 4 and provide evidence to support that choice. So it's not that they have to generate it initially, but I'm going to give them some choices. But so let's unpack this a little bit more. So we know that our original function relationship, these are the five sets of ordered pairs. And we know we've already talked about the fact that the input values are changing, but the output values are staying the same. So when we create that graph, or again, I'm going to look at ordered pairs here. So we look at that and we see that each of them are increasing by 3 units, but we have to keep the output values the same. So what are we going to have to do to the square before the squaring function, since it's happening to the input values, the transformation is happening on the input values. We have to think about this in terms of what is happening to the input values. In other words, before the squaring action, that's going to keep the y values the same. And so if we're going to increase the the input values, but we want to keep the output values the same, we need to put something, we need to subtract 3 before the squaring action to maintain the fact that the output values are going to stay the same. So the functional relationship that shows this is shown above. So if you think about it, you're taking each of those values and you're essentially you're going to take those values now. So like now you're going to substitute in 1. Again, 1 minus 3, quantity squared is 4. And each of those values, now it's 2, 2 minus 3 is negative 1, quantity squared is 1. And so now we've shifted each of those x values 3 units to the right. We've seen that visually in the graph, but we also want to describe that symbolically. So again, this is another strategy that students use oftentimes when I give them a set of choices. We can always fall back on substitution. That's one avenue that students can do this, but we want to move them beyond that, just that point determination, because they may pick a value that may actually satisfy a couple of these function rules. But again, the reality is that we want them to communicate on a more global scale, which is why when we talk about that language, the saying it part, it allows us to do that with a little bit more specificity, as long as we're talking about what is happening to the input and output values and how that aligns with what we're seeing symbolic. So a brief overview. I felt like for the C part with transformation of functions that it's most visible in a graphical representation because it encapsulates all the ordered pairs except for the fact in this case we focused on 5 of those. The table of values allows me to communicate that relationship of why are we taking the quantity, even if we're moving the graph 3 units to the right, why are we putting in the parentheses or the quantity x minus 3 quantity squared? And again, let me say this again. We are moving the input values 3 units to the right, but the output values are staying the same. So we have to think about that. We're still going to square, but what has to happen before the squaring action in order for us to get the same outputs? And you can kind of see that now in the table of values. I think again, that's the seeing it. That's in my mind what makes that most explicit and gives us the best chance of students seeing that part of the relationship. And then lastly, you have the symbolizing part. And again, we've got to see it, we've got the language. And again, that language, let me emphasize again, if we're going to talk about functional relationships and transformations, we need to talk about both input and output values. So a language such as moving it 3 units to the right is not useful to us in terms of getting that functional relationship. Yes, it does describe it, the action, but it doesn't describe the relationship in terms of both the input and output values. So I hope you walk away from this with a little bit better sense of feeling like you can better communicate and transformation functions, but also press students to think a little bit more about the language that they're going to use and attend to precision. And oftentimes that does involve language. So I hope, again, I go back to this is about seeing it, saying it, and symbolizing it. And the saying it part oftentimes is where we lose that sense of precision.